welcome to this lesson. So in this lesson, we want to look at sorts. Okay. So at the end of this lesson, you should be able to define sorts. You should be able to simplify sorts. You should be able to find the conjugate of sorts, and then you should be able to use the conjugate of sorts to rationalize the denominator of sorts. You should be able to solve equations involving sorts. You should be able to tell when two sorts are equal. So this is what we are going to be looking at here. So the lesson is a very simple one. It's a very easy topic. So just follow along and digest the concept. So when we talk about sort, okay, well, of course, let's go into the lesson first. So I've stated the objective, what you should know. So instructional material will be using the chart of sort, using our further mathematics project one and your notebook and writing materials. Okay. So this is a simple chart of sort. This is a chart. Okay. So in this chart, we have the laws of sort. You know, in mathematics, we deal with laws. Whatever you are doing, there's a principle that guides it, and then if you follow the principle, you arrive at the right answer. If you don't follow the principle, you may not get the answer. So this is what these principles are for. So we also have the law of sort, just like we have the laws of indices. Okay. So the rule of sort says root a times root b equals to root ab. When you are multiplying two numbers and they are under the square root, the answer is the same thing as taking the square root of the product. If you multiply the square root of the same number, you get the number. If you do square a root b times c root d, you have ac root bd. You multiply the number outside together, multiply the number inside together, just as if you are collecting like terms. Root a divided by root b is the same thing as root a all over b. When you are dividing separate roots, it's the same thing as dividing the root of the fractional number. Then rationalizing denominator, you can rationalize denominator by eliminating the sod at the denominator. So you multiply numerator and denominator by the sod at the denominator. And then we have another rationalizing form. So this is just a chart. So we'll be making reference to this chart as we continue along. Remember, this symbol is called the root symbol, square root symbol. Is equal to the square root symbol. Okay, square root symbol, and we are going to be using it a lot. So in defining sort, there are other things that we need to know. We need to know all of these parameters that we listed here. Okay, so when we talk about natural numbers, let's take them one after the other. Natural numbers. Natural numbers are like numbers, counting numbers. Natural numbers are counting numbers. Okay, we call them natural. They are counting numbers. They are counting numbers. Okay, number that we use to count. Okay, they are equals to positive whole numbers without zero. Positive whole numbers without zeros. So natural numbers are equal to 1 plus 2 plus 3 plus 4 etc. Okay, so they are counting numbers, or you can define them as positive integers without zero. Okay, so when we talk of whole numbers, number two, whole numbers. So whole numbers are numbers without decimals. Okay, or whole numbers are positive or negative integers. Okay, whole numbers are like positive or negative integers. So positive or negative integers, e.g., plus or minus 1, plus or minus 2, comma is 0, etc. They are all whole numbers. So integer numbers are the same thing as whole numbers. So integer equals to whole numbers. Okay. So these are numbers without decimal points. We have rational numbers. When we say rational numbers are fractions. Okay. They are fractions or exact fractions. Number that can be written as exact fractions or decimals. Okay. Exact fractions or decimals. So that's what we call them. E.g., uh, 2 over 5, 1 over 2, 1 over 4, 3 over 4. They are all exact fractions, because if you change them to decimal, they will give you exact decimal. They will give you a terminating decimal. Then we have number 5, irrational numbers. When we talk about irrational number, it is just like the opposite of rational numbers. Irrational numbers are numbers that cannot be written as exact fractions or decimals. They continue to infinity when you keep dividing them. An example is 2 over 3, okay, 1 over 3, and the pi. Pi is also an irrational number, 22 over 7. Pi is equal to 22 over 7, okay, etc. Okay, before we say etc, let's take other numbers. So root 2 is irrational number, because if you use your calculator, root 2 will continue. Root 3, okay, root 3 or root 5, root 7, root 13, they are all irrational numbers, okay, because they give you terminating decimal. They cannot be expressed as exact decimals when you are dividing them, okay. That's why they are irrational numbers. Hope you are getting what we are saying. Now, when we talk about radicals, radicals are irrational numbers in the form of square root. So radicals are nth root of irrational numbers, okay. So radicals are just like nth root of a. They are also irrational number, but they are in the form of roots. E.g., you can talk about square root of 2 or cube root of 4. You can talk about maybe fifth root of 8, etc. These are radicals, okay. And then finally, our destination, surds. Okay, surds are irrational numbers in the form of square root, okay. Surds are irrational numbers in the form of square root, okay, in the form of square root. So that's the definition. So surds are radicals. They are also irrational numbers, but they are in the form of square root. E.g., if we select the examples we have under irrational numbers, all the square root we have under irrational numbers here, they are surd. Root 2 is a surd, root 5 is a surd, root 3 is a surd, root 7 is a surd, root 13 is a surd, and so on and so forth, okay, etc. So whenever we have irrational numbers or radicals in the form of square roots, they are called surds. Hope you understand the definition now. So that is the simple definition of surd. Surds are irrational radical, such as root 2, root 3, root 5, root 6, and surd are present in solution to some quadratic equations, and so on and so forth. So remember, if we have expression like this, or root 4, square root of 4 is equal to 2. This is not a surd, okay? Root 4 is not a surd. Not a surd. You understand? Root 8. Root 8 is equal to square root of 4 times 2, which is square root of 4 times square root of 2. Square root of 4 is 2, that is 2 times 2, so which is 2 root 2. So therefore, root 8 is a surd. Root 8 is a surd, okay? So, and so on and so forth. We have so many examples that we are going to do. Root 6. Root 6 is a surd because this is root 2 times 3, which is root 2 multiplied by root 3. So root 6 is also a surd. So these are some examples of surd in actions. Okay, so we have so many other examples that we are going to be discussing as the lesson continues. Okay, so we can simplify expression as a single surd. Okay, we can simplify expression as a single surd. We can write expression in expansion form. We can make it simple. We can simplify using addition and subtraction, using multiplication and division. Okay, and so on and so forth. But there are some things that you should know concerning surd. So what are those things that you should know? Or number one, so you need to understand the properties of surd. properties. Number one, that the square root of any surd is always greater than zero. Okay, it is not, surd is not negative. Okay, so and that square root of a, okay, square root of a is real if a is greater than or equal to 0. Okay, so square root of a exists if a is greater than or equal to 0. And also note that square root of ab equals to square root of a multiplied by square root of b. Okay, and of course it is also worthy of note that you should know that square root of a fraction is the same thing as the square root of numerator over square root of denominator, and that square root of a squared is equal to a. Okay, because e.g. square root of 4 is equals to square root of 2 squared, and then you know that square and square root are opposite, so they cancel each other, and then you have 2. Okay, so it follows that way. And then we have so many examples that we can look at in practice. Hope you're getting the gist. It's very simple, so you just follow along. Let's look at simple example, and then we go into what we have next. Examples. Simplify the following. Simplify. Number one, root 11 times root 11. You know that root 11 times root 11 will give us root 11 squared, right? Square cancel square root, and then you have 11. Okay. Number two, root 3 times root 5. Root 3 times root 5 is the same thing as passing 3 and 5 under square root, which is root 3 times 5, which is root 15. Okay, so you can multiply such. Okay, number 3, or 2 root 2 multiplied by root 2 equal to 2 times, collect like terms under the square root 2, which is 2 into root 4, and root 4 is 2, so we have 2 times 2, which is equals to 4. So we have all those examples. So this is how you can simplify sorts. So in our next lesson, we are going to look at simplifying sort proper, addition and subtraction, multiplication and division.